Hello and welcome to another video dedicated to functional groups and chemical reactivity. In the previous two videos, we looked at typical functional groups, and we classify functional groups in different levels according to the number of bonds that the carbon had to heteroatoms. And we also looked at the reactivity, how it was possible to move within the same level, functional group level, from one level 1 functional group to another level 1 functional group, or up and down levels, 1 or 2 levels up or 1 or 2 levels down. And one of the things we discussed in the second video was how a way of going down functional group levels, so moving, for example, from a level 3 to a level 2 or a level 2 to a level 1 functional group level, was by using a nucleophile. And if the nucleophile is a carbon with a nucleophilic carbon, then you will be able to grow the chain. The compound you are making will be able to grow by forming another carbon-carbon bond. And today we are going to be looking at how we can make those nucleophilic carbons, those carbons with a negative charge or a formal negative charge. And we can achieve that by using something called organometallic compounds. So I will share my screen now and we can make a start. This session, as the previous two videos, is based on chemical structure and reactivity and integrated approach by Killer and Ruthers. Specifically, the section I mentioned in the presentation. Also, if you are interested in knowing more about carboanions, what they are, how they are formed, how stable they are, and a little bit understanding the bonding, the molecular structure of those carboanions, I'm also suggesting that you look at section 5.2.2 of Advanced Organic Chemistry by March. Both sections, both chapters are available on Blackboard as a resource to support this video. So the aim of this session is that by the end of studying this topic, both watching this video and studying the chapters I've mentioned, you will be able to predict the product of reactions that involve organometallic compounds, Grignard reagents, and other organometallic compounds. To understand what organometallic compounds are, we need to get our head around what a carbanion is. A carbanion is a carbon atom which has a formal charge of -1. When you have a carbanion and you make it react with an acid, it generates the conjugated acid. And how stable that carbanion is directly related to how strong the conjugated acid that you are forming is. You can imagine the simplest carbanion you can have is the one with one carbon atom coming from a methyl group. So if you imagine this is your carbanion and you have it in an acidic medium, it will react quite quickly to form the conjugated acid, which is the methane molecule. So now, the weaker this conjugated acid is, it means the stronger the conjugated base is, the carbanion is. And the stronger it is, the more stable it's going to be. The more stable it is, the less reactivity it is, because it has a lower tendency to donate electrons. It has a lower tendency to react. So less stable carbanions are more reactive, and more stable carbanions, they are less likely to react. They will find it more difficult to react because they are more stable. They are able to stabilize that negative charge better. Methane alkanes in general are terrible at stabilizing negative charges, and they are actually very reactive. So simple carbanions derived from methane, ethane, propane, that sort of linear alkanes is rare. They are difficult to stabilize. They just don't have any groups, anything in the structure that will help carbon stabilize that negative charge. Carbon is particularly unhappy stabilizing both positive and negative charges. All the chemistry of carbon is the chemistry of covalent compounds. It's not happy making ionic bonds, it's not happy stabilizing charges, positive or negative. In general, for a carbanion to have a certain amount of stability and to be able to form it, you need some sort of delocalization of that negative charge. Basically, your carbon needs somebody to shoulder the burden of carrying that negative charge, either by resonance, by the localization of that negative charge in a pi skeleton, or by having another group, another atom attached to the carbon atom that is able to withdraw some of that negative charge, that is able to stabilize that negative charge, which is where organometallic compounds come about. So, for example, in this example, we have two resonant forms of the same carbanion. And as you can see, the fact that the carbon is able to delocalize this negative charge by using this heteroatom here helps, and forming another resonant form of the same structure helps this carbanion to be a bit more stable. So typically the examples you have here are carbanions that can form because there are or an aromatic structure, or there are groups like the oxygen here and the sulfur that are able to stabilize this negative charge. So the nitrogen here that are able to stabilize that negative charge. So it is not the sole responsibility of one particular carbon to bear the burden of carrying that negative charge. Another way to form carbanions, if you don't have that sort of additional localized structure, those atoms that are able to shoulder the burden of the negative charge, that's, for example, that pi skeleton that might help, like in this case of this carbanion of toluene, to shoulder that negative charge, is by using an atom that is able, that has empty orbitals of appropriate energy, so it's able to absorb, to help in stabilizing a negative charge. And an example of an atom or atoms that have empty orbitals of reasonable energy that can be used is a metal ion. So it is possible to form a carbanion by the formation of a carbon-metal bond. And when you end up is a very polarized bond, sometimes verging in the ionic, and we will explore that further along this presentation. This carbon metal bond is very polarized, and the carbon, the environment of the carbon is electron rich. So it's not shouldering the burden of a negative charge. It is just, it has an excess of electrons around it. These type of compounds, when you have these metal carbon bonds, are called organometallic compounds. And organometallic chemistry sits in the border between organic and inorganic chemistry, because it involves the chemistry of carbon compounds, but when they react with metals. The most typical ones using organic chemistry and used widely in synthetic organic chemistry is lithium, organolithium compounds, and magnesium compounds. And the specific magnesium compounds are called Grignard reagents because of the gentleman that the chemist that came up with their synthesis. They are among some of the most important organic reagents, and they are widely used to grow molecules, to grow compounds, to grow carbon chains. There are other metals used, iron, sodium, potassium, etc. But lithium and magnesium, specifically Grignard reagents, are called magnesium compounds. Organolithium and organomagnesium compounds are the most common ones. Organosodium and organopotassium compounds are essentially ionic compounds. You have this carbon with a negative charge and your sodium or your potassium with a positive charge. There is an ionicity in that. There's a separation of charge. Organolithium and organomagnesium compounds have a sigma bond between that carbon and the metal. It's a very polarized bond, verging into the ionic, but it is a bond. There is a covalent bond. It's just extremely polar because the metal is very electropositive. It is useful for when you're writing organic synthesis and when you're writing a reaction mechanism to think of these organometallic compounds as an ionic, to think that yes, you have a carbon with a negative charge. And that is how they are commonly used when we are drawing reaction mechanisms. However, it is worth keeping in mind that it's only when you're having sodium and potassium you have that truly ionic component of the bond. And for lithium and magnesium, what you have is extremely polar covalent bond. How can you make them? Well, you use magnesium or lithium, the metal of interest, with a halogenated, with a haloalkane in an anhydrous solvent and very inert tetrahydrofuran, THF, or diethyl ether, typical ones. And you can see here this summary of how the reaction looks like when you're using lithium and when you're using magnesium. There are some compounds, some of these organometallic compounds are commercially available, and I've given here some examples from authors of some of the commercially availables. Typically, they tend to be quite unstable. Carbon does not stabilize well negative charges, and they are not particularly stable compounds, and they tend to be synthesized in situ, or at least when they are needed, shortly before they are going to be used, rather than kept for long periods of time. They tend to, especially if there is any trace of water or hydrogen ions, that will break quite quickly the bond. How do they react? Well, they can react either as nucleophile or as a strong basis. In the first example, you have here how they will look, they would act as a nucleophile. The first step needs to be always in an anhydrous solvent, typically ether, THF. You do not want any water. Any traces of water in that medium before your organometallic compound reacts, and you will quickly create the conjugated acid. You will lose that carbanion. But if you're using an anhydrous solvent, then you will have a carbon with a negative charge that is capable of attaching. It can act as a nucleophile and attack the partial positive charge of that carbon. In this example, the carbonyl group. You end up with this intermediate step in which you end up with a salt, a metallic salt, and then in what is called the acid workup, addition of some acid will remove the metal, and you will end up with in this case, for example, the hydroxide, an alcohol, and with that chain that came from the organometallic compound attached to your molecule. So you have managed to grow the carbon chain by adding that carbon chain in the form of an organometallic compound. They can also be used as a strong base, for example, to remove acidic hydrogens, and you end up with a metallic salt that then you might want to use further further on. So in this case, you're not growing the chain as it happened here. As you can see, the carbanion part does not end up in the structure. What you end up is with an alkoxide site, for example, here. So let's have a look at this compound. And you're using this lithium organolithium reagent with 4 carbon atoms. And the first step is anhydrous using diethyl ether, and the second step would be the acid workup using hydrogen ions. I'm going to ask you to stop the video now and try the exercise. See what compound you end up with. Okay, so hopefully you have stopped the video. So now let me see if I can show you how I would do it. You've got the compound that you are looking at. And you're going to make it react with this. And I find it useful to eliminate the lithium or the metal in the organometallic compound and think of the chain as with a negative charge. You have a partial positive charge here in this carbon. You have the negative charge, the formal negative charge, the anion, the carbanion. It can attack quite easily this carbon with a partial positive charge. That means the double bond with the oxygen cannot continue. You cannot have a carbon with 5 bonds. So the electron from the pi bond between the carbon and the oxygen bounce. And you end up with a structure such as this. You've got still this fragment of the molecule. We haven't touched that. You've got your oxygen with a negative charge and the lithium. Let's get the lithium. You've got here this methyl group that is here that hasn't changed. And now you have the extra the fragment, the propane, the propane, the butane fragment that you have created. And it is important that when you add this extra bond that you make sure that you are not losing carbons. So it's always worth counting how many carbons you had in your original carbanion, so in this case 4, and make sure that those 4 carbons are represented again in the compound you are making. It is quite common that when you do these reactions, you end up accidentally, when you make the bond, you end up losing a carbon in the process by mistake. And the second step would be the acid workout. And that is just simply, well, the oxygen with a negative charge is able of capturing a hydrogen ion, and you end up with the compound that you had before. It's not it doesn't have a carbonyl group anymore. It has a hydroxyl group, and it has grown the chain. 2, 3, 4. Yes, it has gone the chain with the butyl fragment that you have added. So this is all for now. If you have any questions or comments, please post in the discussion board or email me, and I will be very happy to answer them. I'm going to stop the recording now. And we will be doing this type of exercise, many more exercises like this one during the sessions we'll have together. So just have a look at the chapter, the chapters I suggested as background reading, and try to do some of the exercises that are proposed in those chapters. And I will be picking up in some of those exercises and similar ones in future sessions. So thank you very much for watching, and I hope this was useful.